Hi everybody! In this video we are going to introduce our first type of special right triangles, the 45, 45, 90 triangles. Special right triangles are triangles that follow very specific rules that we know about the angle measures and the relationships among the sides. This lets us quickly calculate side lengths and angle measures when we know certain pieces of information without having to rely on trigonometry or the Pythagorean theorem. So to understand a 45, 45, 90 triangle, we are going to start with just a square because we know a lot about squares. So I'm going to start by drawing a 3 by 3 square, right? I know it's 3 because I'm drawing on some grid paper and I can measure the side lengths. Now we know in a square that a square has 4 90-degree angles. And we also know that we could draw a diagonal of a square. The diagonal is going to cut across from one corner to the opposite corner. Now we can think about, because a square is symmetric, if we draw that diagonal line, these angles that we've made are going to be 45 degrees. So what we've created is a triangle that has two side lengths of 3, two 45-degree angles, and one 90-degree angle, because that is just the corner of our square. This is why we call it a 45, 45, 90 triangle, because that is the 3 angle measures. Now that we know the side lengths, we could use Pythagorean theorem to calculate the hypotenuse. So I could do 3 squared plus 3 squared equals c squared. 3 squared is 9, so that's 9 plus 9 equals c squared. That's 18. And then I take the square root and we get that c is the square root of 18. Now for special right triangles, we are going to simplify our radicals. So I know that 18 is 9 times 2, which is great because 9 is a perfect square. So we get that the hypotenuse is 3 square root of 2. Now I want you to think for a moment. Do you notice any similarities between the lengths of the sides of the legs of our triangle and the length of the hypotenuse? We might notice that they all have a 3. The hypotenuse has just been multiplied by the square root of 2. That's an interesting relationship that those numbers are so similar to each other. Let's try another triangle and see if that pattern continues or something else happens. So what if we do a 4 by 4 square? I'm going to try to draw a better square this time. So now I have a 4 by 4 square. That's the wrong number. A 4 by 4 square that we can draw the diagonal of. Once again, because we have the diagonal of a square, we know that this is a 45, 45, 90 triangle. And let's use the Pythagorean theorem again to calculate that length of that diagonal. So we're going to do 4 squared plus 4 squared equals c squared. That would be 16 plus 16. So c squared is 32. And we know that c will be the square root of 32. Once again, we are going to simplify these radicals as much as we can. I know that 32 is 16 times 2, so my final answer is 4 square root of 2. So once again, we see that same thing happen, where the hypotenuse is the length of the side multiplied by the square root of 2. Let's try one more scenario, but this time we are going to use variables. So I'm just going to draw some square. Doesn't really matter because this is going to have variables. It's a very bad square. We're going to call the side lengths x. And we're going to calculate the length of the hypotenuse. So I'm going to have x squared plus x squared equals c squared. If I add up x squared and x squared, remember when we're adding up like terms, those have that invisible 1 coefficient. So I have 2x squareds equals c squared. I can take the square root and we get that c is the square root of 2x squared. Now we can simplify this radical as well. I know the square root of 2 is not going to simplify, but I do know that the square root of x squared is just x. So my final answer for c would be x square root of 2. So just like when we had a specific side length for the sides of our square, if we use a variable, we still get that same pattern. And this is the rule for a 45, 45, 90 triangle. In a 45, 45, 90 triangle, we could consider the two legs to be x, some value, and then our hypotenuse, we would take the length of the leg and multiply by the square root of 2. This means that if I know a leg, right? And we could consider those our 45-degree sides because they are across from the 45-degree angle. Then I will multiply by the square root of 2 to get the hypotenuse. So you take, if we're going from the 45 to the 90, so from the leg to the hypotenuse, then you would do times, I'm going to use a different symbol because we've been using x. We'll use the dot. We're going to do times the square root of 2. So what do we think is going to happen if I'm going from the hypotenuse to a leg? If I know the hypotenuse, instead of multiplying, we're going to do the opposite. We are going to divide by the square root of 2 to get the leg. And it's the same legs. So this would go, if I'm going from 90 to the 45 side, I would divide by the square root of 2. So this is if I'm going from the hypotenuse to the leg. One last thing to know about a 45, 45, 90 triangle. So that is a triangle with two 45-degree angles and one 90-degree angle. We could also call this an isosceles right triangles. All right triangles that are isosceles are 45, 45, 90. If you need to draw some examples to kind of confirm that for yourself, you should. But any triangle that has two congruent sides and a 90-degree angle, the other two angles have to be 45 degrees. In the last portion of this video, we are going to practice calculating some side lengths when we know certain pieces. So let's think about it. If I know what my 45-degree sides are, if I know that they're both 2, then to get the hypotenuse, I'm just going to take that 45-degree side and multiply by the square root of 2. So what do you think the side lengths will be if our legs are 7? What do you think the hypotenuse will be? The hypotenuse, we would multiply by the square root of 2, and we would get 7 square root of 2. We can also go backwards. We could, if we knew the hypotenuse and wanted to get the legs, we could divide by the square root of 2. And these square roots of 2 would cancel out, and we would be left with 10.5. And because it is an isosceles right triangle, we know that the two legs are always going to be the same. So down here, we know that these two legs are going to have to match up. So they would either both be 2 root 2 or both 3 root 2. So what do you think the hypotenuse would be if the leg was 2 square root of 2? Well, to get the hypotenuse, we're going to take the leg and multiply it by the square root of 2. So that would be 2 square root of 4, because 2 times 2 gives me 4. That's 2 times 2, because I can evaluate the square root of 4. So that gives me 4. So you notice that now that radical, there is no radical in our hypotenuse because the square roots of 2 were able to become a perfect square. So what do you think the side length is going to be? The hypotenuse is going to be when the legs are 3 root 2. Well, they would be 3 root 2 times the square root of 2, which is 3 times 2, which is 6. So let's try some examples where maybe the radical they give us is not the type of radical that we're looking for. So once again, the two legs are going to be exactly the same. But the hypotenuse, we're still going to take this original value and multiply it by the square root of 2. This is why it's important to know how to simplify radicals when you're doing special right triangles. I can multiply these two radicals together and we get 3 square root of 12. And now that I have that value, I need to simplify. The square root of 12 is 4 times 3, which gives me 3 times 2 square root of 3. So our hypotenuse would be 6 square root of 3. We could also do this by when we're dividing. So because I know the hypotenuse, I'm going to divide by the square root of 2. When you go to divide radicals, you could write those as one big fraction. So I could do 6 over 2, which I know is 3. So my final answer would be 5 square root of 3. In our final two examples, there is something different that's going to happen. Notice that this is an odd number. So when I divide by root 2, notice that these do not divide out evenly. So in theory, this is in its simplest form. In reality, though, mathematicians do not like to leave radicals in the denominator. So what they do instead is they multiply the numerator and the denominator by that radical, right? This is just a version of 1. And they would get 6 root 10 over 2. And now we can simplify the 6 and the 2 to give us 3. And our final answer would be 3 root 10. Now you can try this out. Take this 3 root 10 and multiply it by the square root of 2, and you should get 6 root 5. This process is called rationalizing the denominator. It's about making the denominator a rational number. If you do that for this next problem, your answer would be 3 root 6 over 2. 3 root 6 over 2. And that is how you find the sides of a 45, 45, 90 triangle.